This week we're looking at pressure in gases. Okay, now just to recap, pressure in solids, the pressure equation, pressure is equal to force divided by the area that the force acts over. That still applies, that equation, but now we're going to talk about pressure within a gas. Now to start off with, this presentation just says something to think about. Why do you think a balloon bursts? And as before, if you want to pause the video and give it some thought, but I'm going to move on now. So these are the lesson outcomes. You should, by the end of the lesson, be able to describe the factors that affect gas pressure. Okay, so hopefully you'll be able to describe the factors that affect gas pressure, and then describe how atmospheric pressure changes with height. Okay, so a balloon. What are the differences between a fully inflated balloon and a partially inflated balloon? Now, to discuss this, or to demonstrate this, the video will cut to me looking at a partially filled inflated balloon and a fully inflated balloon. So we'll move on to that now and come back to this after that. Okay, so here are two balloons. One balloon's more inflated than the other. The reason being is this balloon I've blown in a lot more air into that balloon, okay, and the air inside there is higher pressure than the air inside this balloon, and there's a number of reasons why something might have higher pressure internally, but in general, no matter which balloon, there is an internal pressure due to the gas molecules moving around inside and making collisions with the inside wall of the balloon, and each collision exerts a force on the area of the wall. So pressure is the force per unit area, so gas pressure comes from these collisions of all these tiny little gas particles moving around and hitting off the inside of the walls. The reason why this one has higher pressure is because we've actually physically managed to put more gas inside this balloon. Okay, so this balloon has more air molecules, so that means that the chances of them colliding with the wall are more frequently, so this has higher pressure. The gas in this one from the air, it's just air from my lungs, it's not colliding with the internal walls that much. Okay, so this one's higher pressure because of the amount of gas molecules I've put in. Okay, so we watched the video on the two balloons, the fully inflated balloon and the partially inflated balloon, and we discussed the differences. So hopefully that's give you a bit of an insight into pressure, and let's discuss this in a bit more detail with a diagram. So this page has two diagrams in. One diagram is of a container with a larger container with the particles, the gas particles moving around, but they're spread out because the container is much larger. And then the diagram next to that, there is a small container, and if we had the same amount of gas in there, what would happen is that gas, the particles that make up that gas, would have a lot less room, and so they would be colliding with the inside of the container more frequently than the larger container for the same number of gas molecules. So this was an investigation that would have been done in class. It says, investigating gas pressure. Two short experiments can be used to demonstrate the effects of atmospheric pressure, the collapsing bottle and the sealed syringe. Write down your observations for each experiment and use your knowledge of gas pressure to explain your observations. So I am going to demonstrate a collapsing bottle, a sealed syringe, and I also have another demonstration I'm going to show. By all means, if you want to write down the observations, but you can just watch and listen to my explanation. Here's the bottle demonstration. So we're putting hot water into the bottle. That hot water will make the air inside it expand, get hotter, get more energetic. The pressure will increase and the air will hopefully move out of that bottle. And then once I put the lid on, the the leftover air inside is less than the air outside, so as it cools, the actual pressure inside the bottle will be much lower than the external pressure of the atmosphere, and so the external pressure from the atmosphere is applying a force on the bottle that is crushing the bottle. Now this was recorded in time lapse after I put the lid on because it took a long time for the gas inside to cool and for the pressure internally to go down enough so that the external pressure from the atmosphere crushed the bottle. This time, once I put the lid on the bottle, I'm going to submerge the bottle into a bucket of cold water. Now what that's going to do is the leftover gas inside the bottle that was a fairly high pressure in comparison to the outside. This is going to now cool quickly, and the pressure is going to go down more rapidly, so the external pressure on the bottle is going to squish it much quicker than before. Okay, here's the syringe. Now you've got a plunger that you can pull out and push back in. Now that plunger, as you move it out, this chamber becomes larger, and what happens is the air outside, the air pressure pushes air into this chamber. Okay, that's pretty easy to do. However, if I put my finger and block the end, if I then try to pull the plunger out, what's actually in here now is a vacuum. Okay, maybe a tiny little bit of air from the fact that this part of the chamber had some air in. But we've essentially got almost a vacuum, void of air, so there's low pressure inside the chamber. And because there's low pressure inside there and the air on the outside has high pressure, that should apply a force and push the plunger back. So if I pull this out, which is quite hard to do, and then I let go, you see the plunger goes back? That's the external pressure from the air pressure that's pushing that plunger back. And if I were to let go of the end of this syringe, what would happen is air pressure outside, the high pressure, would actually push air into the empty chamber. So you should be able to hear that. Okay, I'll do that again. You can hear that air rushing. Final thing to point out is that if I do trap some air in here, okay, what you can do is you can actually compress the air, because a gas can be compressed because the particles in the gas model are spread apart, so there's gaps for you to actually squish them together. And then notice the opposite effect now. Because I've pushed this and I've squeezed all those particles close together, there's more collisions inside that container now, and so the pressure inside is higher. So when I let go, it pushes the plunger back out, because the external pressure at that point is less than the internal pressure. So the bigger force is pushing out until eventually it reaches this equilibrium position where the forces are balanced. Okay, I've got the syringe and I've got a very tiny amount of marshmallow. What I'm going to do is I'm going to put the marshmallow inside the syringe, and then I'm going to squish that down, put my finger on the end, pull the plunger out to form a vacuum, and we're going to see if anything happens to the marshmallow. Okay, let's have a look. It's very sticky, so this might be pretty difficult to do. Let's see, push that in. So obviously the air is being pushed out. Okay, now what I'm hoping is that inside this vacuum, when I create it, or a lower pressure, because there's some air in there to begin with, hopefully the internal air within the little tiny bubbles and pockets within the marshmallow will push out, because the marshmallow will have a high pressure inside it compared to the outside pressure in the tube, and that pushing out, you should see the marshmallow expand. Okay, so let's see, are we ready? Okay, you can just about make that out. Okay, so the marshmallow, as I reduce the pressure internally, it expands, and then if I let the air come back in, maybe the external air pressure that's higher we'll rush in and maybe squish the marshmallow. There we go. Okay, slightly different experiments. I've got an egg and a bottle, a milk bottle. I'm doing the same things I did before. I'm putting hot water in, but this time the glass bottle is quite rigid in structure, and so it's strong enough to not be crushed. But if I put an egg on top, so remember that we've got low pressure as the air inside cools and high pressure outside. What's happening is the high pressure outside is squeezing the egg into the glass bottle. It's the same demonstration now, but to speed things up, this time I use some fire to heat the gas inside. This gets the particles inside much hotter. The pressure internally is increased, so the gas kind of escapes around the sides of the egg, and then as soon as that starts to cool, the pressure drops and the external pressure from the atmosphere pushes the egg into the milk bottle. In this demonstration I've got some water on a plate. It's coloured purple just so you can see it more clearly. I'm going to light a match and light a candle. The candle will then give off heating air in a glass that I put over the top. The air inside is initially high pressure and some might be pushed out from under the glass, and then as the air cools it forms low pressure, and the higher pressure externally to the glass will push the liquid up into the glass. Okay, so having watched the demonstration for the collapsing bottle, here are some questions we can ask ourselves. How does gas pressure change with temperature? How does this cause a bottle to collapse? Why couldn't you pull out the pump of the sealed syringe? And how does atmospheric pressure change with altitude? Okay, let's answer these questions then. So, how does the gas pressure change with temperature? Well, you noticed when I put hot water into the bottle, okay, so the gas within the bottle heated up and it expanded, and that gas left that bottle because it was a high pressure within the bottle, and that escaped into the lower pressure atmosphere around the bottle. And so at that point we can say that the gas pressure does increase with temperature. We're giving the particles more energy to move around. They'll therefore make more collisions with the inside of the bottle, and more collisions equates to a higher pressure. How does this cause the bottle to collapse? Well, once that high pressure has kind of pushed a lot of the air out, and then we seal the bottle, what happens then is the leftover gas inside that was at high pressure will start to cool. And if pressure increases with temperature, well, as it's cooling, the pressure goes down. So inside the bottle, there will be a low pressure, and then the higher pressure around the bottle on the outside, the atmospheric pressure, will apply a force across that area of the bottle, and it will crush it because the outer forces are greater than the inner forces. Why couldn't you pull out the pump of the sealed syringe? Okay, so when I put my finger over the end of the syringe, I found it hard. I mean, I could pull it, but it was difficult to pull it up. And so that's because internally, because the volume of the container is increasing, the pressure inside, because it was sealed for a fixed amount of gas, that goes down. So the pressure inside the tube goes down, meaning that the pressure outside, the atmospheric pressure, is larger than the pressure inside. And so that external pressure will apply a force and push against the plunger, pushing it back in. So even though I'm trying to pull it out, there is an external force pushing it back. And when I let go, you saw that syringe plunger move back because it was being pushed back in by the atmospheric pressure. How does atmospheric pressure change with altitude? Okay, in this final one then, the atmospheric pressure altitude, meaning that the height of the atmosphere above. So as we go higher up, what happens is there is less gas above us. Okay, so the air on the ground is very dense because of all the weight of the gas above, all the weight of the atmospheric pressure above. So when there's a lot of gas and there's a lot of particles pushing together, you're going to have a high pressure lower down, and as you increase your height, as you move through the atmosphere, as the atmosphere becomes less dense, there are less gas particles moving around, creating a lower pressure. So the atmospheric pressure goes down as you increase height above the surface of the Earth, so as you go up through the atmosphere. Okay, so I will leave these questions. I've got some questions that will come out on Wednesday for your assignment, so please have a look out for those. And let's just recap. Gas pressure is the force exerted by gas particles colliding with surfaces. So for instance, inside the bottle, the air was bouncing off the inside of the walls, and those collisions were exerting a force on that surface, and that's what gas pressure is. Compressing a gas or heating a gas will increase the gas pressure, something not mentioned but I showed in a demonstration. As I try and compress the syringe, if I trap some air in there to begin with, you can compress a gas, you can squeeze it into a smaller space, so then therefore there are more collisions with the wall. The rate of collisions goes up, so the pressure goes up. So as you compress a gas, the pressure goes up. Atmospheric pressure decreases with altitude. Okay, so as I said in the last slide or the slide before, as you increase height through the atmosphere, as you go up, the density of that gas gets less and less, because there's less atmosphere above pushing down, and so the pressure decreases with height. And then finally, air has a higher density at sea level. So density is just how many particles are fitting within a certain volume, and so there are more particles at the surface of the Earth because they're being squished on by the particles above them. And so the density of air is denser at sea level than it is if you went up very high into the atmosphere. Okay, I hope this helps.